everyone. Welcome back to this second session of the second day. What I would like to talk about in this session is the topic of non-smooth problems. Okay, so far we've looked at problems where we can take a gradient and where we can sometimes even take a Hessian. I mean, I talked about the Hessian even though it was not involved in the algorithm. But essentially where we can define a notion of gradient, a notion of derivative. But in many problems in data science and otherwise, we face objective functions or constraints that are not smooth. Okay, where the notion of gradient or the notion of derivative is not well defined. Okay, and I've explained, I've given some examples in the first session. For example, the lasso problem, where you want to solve a least squares problem, but with a certain regularization to ensure that the solution is sparse. We saw that we used an L1 regularization term. Okay. Also, a common function that shows up when modeling problems in either data science or engineering and so on is the L infinity norm. So this is the maximum of the absolute values of xi. Again, that is not a smooth function. And in general, any function that you define as the max of some other functions, that's not going to be a smooth function, because at the boundary, when two functions in the max are equal, then this is typically going to be a region where the function is not differentiable. Okay, so the gradient is not well defined for these functions. The analysis of the gradient method I did relied on smoothness and so on. So everything I have discussed in the last two lectures does not apply to optimization problems involving things like the L1 norm and so on. Okay, so what I would like to do today is, so this is particularly an important problem in data science, exactly because of the ubiquity of such non-smooth regularization terms, things like the L1 norm. Another function that shows up a lot in imaging especially is something called the TV norm. Okay, so the TV norm, the total variation norm, is something like, maybe I can write it this way. So this is the sum from I equal 1, let's say, to n minus 1 of the absolute value of xi plus 1 minus xi. Or it's also defined if x is a two-dimensional image. So this is used a lot when you want to recover an image. So let's say you have a certain image that is noisy, and you would like to denoise the image. So you'd like to remove the noise. So a certain prior information that you have about the image is that the image is typically consisting of piecewise constant regions. Okay, so regions where the color or the grayscale level doesn't change very much. Okay, and so imposing a total variation regularization in your objective function will exactly impose that xi plus 1 minus xi is sparse. So the difference vector, this discrete derivative, if you want, is going to be sparse. And so this means that in regions, so xi will be equal to xi plus 1, and then suddenly you'll have a certain jump whenever you need to have such a jump. Okay, so this is another function that is used a lot in imaging. So this is used in imaging. Okay, this is for, let's say, for denoising problems. And so, such non-smooth objective functions have become very prominent in these areas related to data science, imaging, and so on. And so that's why the research in non-smooth optimization has grown accordingly. So people have developed in the last 10 or 20 years new techniques to deal with such problems. So this has been an importantly especially important focus in data science. So so what I would like to do today is to first give you, to first present the basic tools that we need to be able to, the mathematical tools that we need to be able to deal with such problems. And so today I will present probably the most basic algorithm to deal with non-smooth problems, which is called the subgradient method. It is a very simple method. It's also a one-liner. It's actually very similar to the gradient method, except that instead of using a gradient, you use a subgradient. We will see, however, that its performance is quite poor. So it is quite slow. You need a lot of tuning of the step size. The choice of the step size is highly non-trivial. So we'll look at this. Okay. So it's not a method that is very attractive. So what we will do tomorrow morning is I will present to you another method that is typically a method that is used in practice, something called the proximal gradient method, and that exploits a little bit more than just non-smoothness, that exploits some structure in the objective function that you want to minimize, something like a splitting structure. So if the objective function you want to minimize is the sum of something that is smooth and something that is non-smooth, but that is a relatively simple function, but non-smooth, something like the L1 norm, then we have a good algorithm called the proximal gradient method that typically performs much better than the subgradient method. Okay, I will talk about this tomorrow, but today what I would like to do is just to first introduce some of the mathematical notions that are needed to talk about such non-smooth problems. Okay, and in particular, I'd like to introduce the notion of subgradient to be familiar a bit with it, and then to use it in the analysis of the subgradient method. Okay, so let's go on. So we've seen that if f is a smooth convex function, so if it's continuously differentiable, just in this case, then the gradient satisfies the following property, that it gives us, it allows us to get a global lower bound on the function f. So at any point x, I can construct a global lower bound on my function by looking at the first order Taylor approximation. So we said that if I have my function, so this is my function, and if I construct a Taylor approximation at this point, okay, then I get a lower bound. I can construct a Taylor approximation at another point. That's also going to give me a lower bound. I can construct at a third point. Okay, it's going to give me a third lower bound. Okay, so these lines, they are all Taylor approximations of my function at different points, and they're all global lower bounds on my function. Okay, so now how do I define, if my function is not differentiable, I cannot talk about a Taylor approximation around that point, if my function is not differentiable at a certain point. Okay, so so the notion of subgradient is not defined in terms of a Taylor approximation, but it is defined in terms of this property of being a lower bound on the function everywhere. Okay, so we say that if you take a certain point x, okay, of your function, so in the domain of your function, then we say that g is a subgradient of f at x if the following inequality is true for all y. So if f of y is bigger than f of x plus g transpose y minus x. Okay, so this is exactly like the Taylor approximation that you see at the top here. Okay, the only difference is g instead of gradient of f at x. Okay, so any g for which the resulting linear function is a global lower bound on f is going to be called a subgradient. Okay, so for example, obviously the first observation is if f is smooth at x, then the gradient of f at x is a subgradient. Okay, so maybe I should have written this here. So if f is smooth at x, then the gradient of f at x is a subgradient at x. Okay. So now, but if f is not smooth, obviously now the interesting question is to know if f is not smooth at x, what are the subgradients? And this is what we'll explore together. Okay, so the set of subgradients of a function at a certain point is called the subdifferential, and it is denoted by this notation, this partial f of x. Okay, so so partial f of x is the set of vectors g such that g is a subgradient of f at x. So now, why did I define it as a set? Because it is, I do not know a priori what, so I just defined that G is a subgradient of f at x if this is satisfied. And we will see, in fact, that the subgradient is going to be a set, that in general, for non-smooth functions, there may be many vectors G that will satisfy this yellow condition that you see here. Okay, so let's look at an example. Probably the simplest example that we look at. So let me look at the function, the simplest non-smooth function, which is the absolute value function. Okay, so this is the function absolute value. Okay, so obviously now if I take a point x that is positive, okay, and I want to construct a lower bound, a global lower bound on f, okay? So if I want to construct a global lower bound on f, so it is easy to see that the slope of this line has to be equal to 1, okay? There is no other way, okay? So this means that the subdifferential of f at x is equal to +1 if x is positive. Okay. In fact, if x is positive, you can see that the function is smooth. Okay, and the slope is equal to 1, and this is the only thing that you have in the subgradient, in the subdifferential. Okay, this is the only. So if I write this way. Okay, so this is the only possible choice of g that will give you a lower bound. If you choose another slope. Okay, so if you choose a slope like this, so something smaller than 1, you see that this is not going to be a lower bound on f because it's above f in this region. Okay, and if you use a slope that is bigger than 1, okay, so if you use something like this, then you see that this is also not going to be a lower bound on f because it's going to be above f when for y is bigger than x. Okay. So the only possible lower bound is to choose a slope equal to +1. Okay. Okay. So let me delete this part. And, so let's actually, maybe I should write here the definition of subgradient. So I want f of y to be bigger than f of x plus g times y minus x. Okay, so here there is no, here it's in one dimension, so g transpose y minus x is just g times y minus x. So g is really the slope of the line that I'm going to draw. Okay, so the same observation that I did for x positive is true for x negative. So you can see that df of x is going to be equal to -1 if x is negative. Okay, so if I take a certain x that is negative, okay, so then the only lower bound I can construct on my function, the global lower bound I can construct on my function is this line. Okay. So okay, so now obviously the main interesting question is what happens at the point 0. Okay. So what is df of 0? Okay, so I have to think in order to understand what is the set of subgradients at 0, I have to understand what are the possible lower bounds, global lower bounds on my absolute value function. Okay, so let me draw for you several lines that will actually be a lower bound. So here is one line. Okay. This is a global lower bound on my function. This is valid. Okay, this is valid. This is valid. Okay, this is valid. Okay, so you can see that. Okay, sorry, my drawing is not so super nice here, especially. Okay, so kind of you can see essentially. I mean, now I think you get the pattern. You can see that any line whose slope is has absolute value less than 1 is going to work. Okay, so you can see that df of 0 is essentially just the interval minus 1, 1. Okay, so I don't have to write this. Okay, so at the point 0, okay, this means essentially at the point 0, I can draw any line with a slope that is between minus 1 and 1, and this is going to give me a lower bound on the absolute value. Okay, another way of saying this is that the absolute value of y is bigger than g times y for any g in minus 1, 1. Okay, so this inequality here is exactly the inequality that you see at the top. So maybe you see this inequality at the top and this inequality here. Okay, these two are the same when x is equal to 0. Okay, and so for any g between minus 1 and 1, this highlighted inequality is true. So this tells us that the subdifferential of f at 0 is really the interval minus 1, 1. Okay. Okay, so I hope that was clear. Okay, this is a bit. I draw a bit too many lines here. So okay, so I hope that was clear how to that the subdifferential of f at 0 in this case was the interval minus 1, 1. So these are the set of valid slopes that you can have. Okay, so so let's now look at another example. So let's look at, for example, the function f of x is equal to the 2 norm of x. Okay, so this is equal to so x1 squared plus x2 squared plus up to xn squared, and then I take a square root. Okay. So so here x is in Rn. So f is, you can show that f is differentiable when x is non-zero. And in this case, the gradient of f at x, okay, it's not so difficult to prove, it's just x divided by the norm of x. Okay. So now, obviously, the question is what happens when, what is the subdifferential, what happens at 0? So the definition, so df at 0, the set of subgradients at 0, is the set of G, okay, such that f of y is bigger than f of 0 plus G transpose y minus x. Okay, so I can simplify this. So this is the set of G such that a norm of y is bigger than f of 0 is 0. Okay, and so x is equal to 0 as well. So this is bigger than G transpose y. Okay, and so it's the set of G, the set of vectors G is such that G transpose y is less than the norm of y. And it is a simple exercise to see that this is exactly the set of G such that the norm of G is less than 1. Okay, and this is okay. So I should have written here. This has to be true for all y. Okay, and here for all y. Okay, so you can show that this is true, and here this is by an application of Cauchy-Schwarz. Okay, because if the norm of G is less than 1, then G transpose y is less than the norm of G times the norm of y, which is less than the norm of y. Okay, this is by Cauchy-Schwarz. So this shows one inclusion. Okay, and the other inclusion is also not so difficult to see. Okay. So this tells us that then the subdifferential of f of this norm function at the origin is exactly the L2 ball. Okay, the L2 unit ball. Okay. Okay, so let's now move on and look at some properties of this subdifferential map, okay, the set of subgradients of a function, okay. So you can prove, and this is already non-trivial, I will explain a bit how to prove such a result, that if a function is convex, then its subdifferential is always non-empty, that you can always find a vector g, okay, that will give you a global lower bound on the function. Okay, so you can always find a certain g at any x, such that f of y is bigger than f of x plus g transpose y minus x. This is obviously not true for non-convex functions, but for convex function, it turns out to be true. And I will explain how one can prove such a result. You can show, and this is not so difficult to prove, I will also show how to do this, that if f is smooth already at x, then the subdifferential is just consists of one element, which is the gradient of f at this point x. Okay, so then we have some calculus rules, just like the gradient. If I compose f with a linear function, ax plus b, then the subdifferential of at g at x is A transpose the subdifferential of f at ax plus b. Okay. And this is like the gradient. Now, if you add two functions, if you have two functions that are convex and you look at the subgradient at f1 plus f2, then this turns out to be the sum of the two subdifferentials. And by the sum here, I really mean the Minkowski sum of the two sets. So meaning that you take any element from the first set and any element from the second set, and you add them up. And this will give you a valid subgradient of f1 plus f2. Okay. Okay, and this last one is very important as well. So if you have a function that is defined as a maximum of other functions, which is very often the case, then in order to compute a subgradient of the function f at a certain point, so what you do is that you find so essentially which I achieves the maximum. Okay, so you find so you find here which I achieve the maximum. Okay. And then you take a subgradient of one of the i's that achieves the maximum. That gives you one way of computing one subgradient. Okay, in order to compute all possible subgradients, you have to look at all possible i's that achieve the maximum, and then you take the convex hull of the union of all these subdifferentials. Okay, so it's a bit more complicated, but in many situations, we actually only need one subgradient. We need to be able to exhibit just one subgradient at the point x and not to have all possible subgradients. Okay, so I will go again over these. I mean, I will try to explain what is involved in the proof of this. Especially, I want to just kind of talk a little bit about the first point. Why is it that I can always find a subgradient? Because this is related to something very basic about convex sets. And so this is something called the separating hyperplane theorem. So what is the separating hyperplane theorem? So it tells you something something fundamental about convex sets. The thing is that if you take any convex set C, okay, and you take a point that does not lie in C, so I take a point X that does not lie in C, then I can find a hyperplane that will separate X from C. Okay, so if C is convex and X is not in C, okay, so then this implies I can find, okay, a certain vector, I don't know, call it Z, for example, okay, such that, so Z transpose X is bigger than some constant B, and Z transpose Y is going to be less than B for all Y in C. Okay, so this means that if I call this if I call this guy, this is the hyperplane Z transpose Y is equal to B. Okay, so and Z is this vector. Okay, so what these inequalities are telling me really is that Z transpose X is on one side of this hyperplane, and the convex set C is on the other side of this hyperplane. Okay, so this is what we call the separating hyperplane theorem. And so the proof of this theorem is actually not very complicated. So the proof of this theorem, it's actually easy to see geometrically what you would like to do. So the Z, the way you want to choose the Z is essentially you take this X, you project it on C, okay, and this Z is going to be proportional to X minus the projection of. So if this is pi C of X, okay, so you take Z to be essentially just X minus the projection of C on X, okay, which is non-zero because X is not in C. Okay, I will not give the details of the proof, but this is really geometrically what happens. So this is what you take, and then you can, this allows you to construct the separating hyperplane. I mean, this theorem is a fundamental theorem in convex analysis and convex geometry. It underlies many of the results about duality and so on that we will talk about tomorrow. Okay, and one particular application is actually to prove the existence of subgradients. So let me tell you how this is done. So so first, before I talk about subgradients, let me talk about something else called the supporting hyperplane, which is another important concept. So if I have a convex set C, okay, and I take a point on the boundary X, okay, so C is convex, and X is on the boundary of C, okay, then a supporting hyperplane is something that will, what as its name suggests, it will support the convex set at C. Okay, so it will look like this. Okay, so essentially you can think of it as a tangent, to the convex set C at X, except that the set C does not have to be kind of smooth around X. So let me draw another picture. So let's, for example, assume that my set has a kink somewhere in here, okay, that it looks like this. Okay, this is another point X. So I can have, you can see that here I will have many different possible supporting hyperplane. So I will have one like this, and so on. Okay, so these are all possible supporting hyperplanes. Okay, so more formally, a supporting hyperplane. So a supporting hyperplane at X, okay, is a hyperplane, so defined by a certain vector, is a hyperplane, so such that A transpose X is equal to B, okay, and A transpose Y is less than B for all Y in C. Okay, so it's a hyperplane that goes through X, okay, and yet and the convex set is all on one side of the hyperplane. Okay, you can prove the existence of a supporting hyperplane using the separating hyperplane theorem by essentially separating X from the interior of C. Okay, so you look at X and you look at the interior of C. These are, the interior of C is an open convex set that does not contain X, and you apply the separating hyperplane theorem, this will give you what you want. Again, I will not prove, I will not give the technical details of the proof, but this is essentially how it works. So how do you, okay, so I need a bit, some more pages here. So how do you prove okay, so application, okay, so application, so how do you prove, 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 okay, so application, so how do you prove of the supporting hyperplane to the existence of subgradient. Okay, so what you do, so I'll do the one-dimensional picture, which actually just generalizes to the higher dimension. So let's say I have my function, okay, and I want to, this is my point x, and I want to show that there is, there exists a subgradient. So obviously here we do see that there exists a subgradient. For example, we see that this line is a global lower bound on my function. Okay, so how do you actually do this? So it is very simple. By applying the supporting hyperplane theorem to the epigraph. So remember the epigraph. What you do is, so recall that the epigraph of f is the set of xt such that t is bigger than f of x. This is the thing that you see in green here. Okay, so now I know that x, the point x f of x is in the boundary, lives on the boundary of this epigraph of f. Okay. And so obviously we know that this epigraph is a convex set. Okay, and I have a point on the boundary, so I can construct. Okay, I can. So this means that I can construct a supporting hyperplane to APF at the point x f of x. Okay, and this is exactly this supporting hyperplane, as you can see in the picture, as it is visually clear, that this supporting hyperplane is going to give you the subgradient. Okay, so this, you can see that this is supporting hyperplane to APF at x f of x. Okay, what you just have to do, you have to extract the slope of this line, and so you can do this in a simple way. Okay, I will not do the details again. So okay, so yes, so this was one thing I wanted to mention. Let's see, I wanted also to say some other things. Let's look at this slide here. Yes, so okay, let me mention two other things. So okay, so it is clear. I mean, I will not kind of explain too much, but if f is smooth at x, then the subdifferential of f at x just consists of one thing, which is the gradient of f at x. Okay, again, this is kind of clear if we draw a picture. So if I want a global lower bound on f, the only thing I can take is really just the derivative of f. Okay, if I deviate a little bit from it, I will definitely be either an upper bound or a lower bound. Okay, so I really have to take, there's just a single line I can draw here, and that the line will have to be the first order Taylor expansion. Again, I'm kind of trying to give just some intuition about these things without writing formal proofs, because I hope most things here are relatively intuitive. So let me again just illustrate one more fact about the subgradient, which is the subgradient of a max of functions. Okay, so if I have f of x is the max over I in I of some other functions fi of x. Okay, so to construct a subgradient of f at x, what you do is that you find I in I such that f of x is equal to fi of x. Okay, this is the argmax thing, and then what you do is that you take g in the subdifferential of fi at x. Okay, so this will give you one subgradient, and again, if you take all possible i's and you take all possible g's and you take the convex hull of all of this, then this will give you the full subdifferential. Let me illustrate this with a picture. So the simplest picture of a function defined pointwise is a polyhedral function. So so you have something that looks like this. So okay. So here, this is a max of 4 functions. So you can see, I mean, 4 linear functions. So this is f1, f1, f2, f3, and f4. Okay, so f1, f2, f3, and f4 are 4 linear functions. Okay, and so if I define f of x to be the max of these 4 functions, f1 of x, f2 of x, f3 of x, and f4 of x. Okay, so then the graph of this function, maybe I can, the graph of this function is exactly going to look like this. So here f1 is the largest function, so I'm going to be like this. Okay, and then in this space, f2 is larger, so I'm going to look like this. Okay, in here f3 is the largest, so this is okay, and f4 here is the largest, so I guess I should have chosen a stronger, something like this. Okay, so this is my function f in purple, that you see in purple here. Okay. Okay, so now what is the subgradient of f? Let me write it in calligraphic. So what is the subgradient of my function f? So let's try to understand this. So if I take a point, so let's try different points. So if I take a point, let's say a point x here, then you can see that the function that I'm actually looking at is really f4, okay, and f4 is differentiable in this function in this region. So there is just the subgradient is really just the slope of f4. Okay, so let's so if I write so if fi of x is equal to ai x plus bi, let's say, okay, so so then the differential of f at x for this specific x, let me call it just x4, okay, df at x4 is just going to be equal to a4, okay, because 4 is really this is the 4th function that is really active in this region. Okay, if I take another point, let's say if I take if this is another point, let's say I call it x3. Okay, so here at the point x3 there are 2 functions that are active, and so this means that there are 2 I can choose. I mean, f3 and f4 have the same value at x3, So I can either choose as a subgradient the slope of f4 or the slope of f3. And these are two valid subgradients. And in fact, anything in between these two slopes, so the convex hull of the two, is going to give me all valid subgradients. Okay. Okay, and so on and so forth. So I hope this is clear. In fact, this is exactly what happened when we did the absolute value example. The absolute value, you can write it as the max of x and minus x. And at 0, these two are equal to each other. And so the slope is anything between -1 and 1. Okay, anything between the slope of the first function and the slope of the second function. Okay. So okay, so I hope that is kind of okay. I mean, it is clear that really the important notion is that the subgradient always gives you a global lower bound on the function. And obviously something that I did not say, but it is obvious that if the zero vector is a subgradient, if the zero vector belongs to the subdifferential, then x is a global minimum for f. Okay, this is because what I have is that f of y is bigger than f of x plus 0 transpose y minus x is equal to f of x. Okay. So this is equivalent to the condition that the gradient of f of x is equal to 0. Here you require that 0 has to belong to the subdifferential. Note that there could be other things. The subdifferential could contain other elements other than 0, and x still being the global minimum. So this is the example of the absolute value. The 0 point is, let's go back here to the absolute value. Okay, so the global minimum is the origin. So you can see that 0 does belong to the subdifferential, but there is also other elements in this subgradient, in this subdifferential, which are non-zero. So this is one difficulty of the subdifferential compared to the gradient. Okay, so now let me talk about the subgradient method. So now I want to minimize a function f of x, and f is not smooth. Okay, so the subgradient method is a very simple method. So you start from a certain starting point x0, and you iterate xk plus 1 is equal to xk minus a certain step size tk times gk. And gk is any subgradient of f at xk. Okay, so instead of taking a gradient, you take a subgradient. So okay, for many of the points that you will encounter in the algorithm, the function will actually be differentiable. So you just take the gradient of f at xk. If you're at a certain point where it's not differentiable, then you just take any subgradient, and this is what you put. So the iterations are very cheap. Okay, so it is easy to see right away from the example I just gave about the absolute value that this method is not going to be a descent method in general. Okay, so it is possible that the value of the function f at xk plus 1 is going to be bigger than the value of the function at xk. This can happen if you choose the wrong subgradient. I mean, there's no wrong subgradient, but if you choose a bad subgradient. So let's say, for example, that your function f of x, that your function f is the absolute value. Okay, and let's say that your iterate actually you happen to be at the origin, xk is equal to 0. Okay, but you happen to take a bad subgradient, so you take gk, let's say, is equal to plus 1. Okay, which we saw is a valid subgradient of f at xk at the origin. So then what will happen, even though you started at the minimum, okay, what will happen is if this is xk, then your xk plus 1 will actually move away from the origin. Okay, so and definitely your function value will actually increase. Okay, so so the direction gk is not necessarily a descent direction, a direction where the function value will decrease. Okay, so this is the subgradient method. It's probably the simplest method for non-smooth optimization. the convergence of the subgradient method is kind of tricky. In fact, in general, it is not a convergent method. It will not, in general, converge to the optimal value unless you choose the step size very carefully. Okay, and this is what I mean by this is that if you choose the step size to be constant, we will see that in general you will not get convergence. So you have to choose it to be decreasing in a certain way. So so this is the basic convergence result that I'm going to prove. It's actually very simple, so it will just take a couple of lines. Okay, so so here f best k, this is the minimum of f of x0, f at x1, etc., f at xk. Okay, I'm not consistent with the notation for f. So so it's the best value seen so far. The reason why you consider f best k instead of f of xk is because the method is not a descent method. So it could be that so iterates are not monotonically decreasing. So that's why I need to consider the best iterate so far. So what one can show is that f best k minus f star, so the gap in function value, is bounded by the following quantity. Okay, so this quantity looks a little bit complicated. I'm going to dissect it. Actually, let's see now. Yes, so I'm going. Let me kind of dissect it a little bit now, and then we will see how to prove this. How to prove this result. Okay. So so let me just rewrite it here. So what I have is f best k minus f star. This is less than, so the norm of x0 minus x star squared divided by the sum of ti's plus g square, I think. Yes. G square sum of ti squared divided by the sum of ti. Yes, okay. So this is what we can prove. So let's first look at what happens if you have a constant step size, the simplest regime. Okay, so if you have a constant step size, then in this case, so ti is equal to t. Okay, and so in this case, the upper bound can be simplified. So what you get is this divided by 2 times k plus 1 t plus g squared. Okay, and then what I will get is k t squared divided by k times t. Okay, so I will get g squared times, so let me just write it. So k plus 1 t squared divided by k plus 1 t. Okay, so in general, this thing will actually simplify to just g squared times t. Okay, so just write. So this is just g squared times t. Okay. Okay, I guess there was maybe a yes. Actually, I think there is a 2 now that I look at. I think I forgot the 2 here, so there should be a 2 here, but it's not super important. It's fine. Okay, so so you can see that if I let k go to infinity, what is going to happen is that the first term, okay, so this term will go to 0 as k go to infinity. Okay, but this term actually does not go to 0. This term does not go to 0. Okay, so this means that I cannot prove a priori that that my function value is going to converge to f star. Okay, but it is going to converge to a neighborhood of f star. So it's going to converge to a neighborhood whose size is proportional to g squared t divided by 2. Okay, where G, maybe I forgot to mention it, even though it was written on the slide, G is the Lipschitz constant of the function f. Okay, so now let me okay, so let me talk about a different regime of choice of step sizes. Okay, so what you can do, so a regime that is often considered, so if you choose Ti to be some constant divided by the square root of I plus 1. Okay, this is typically the choice of step size that is used for this method. Okay, so note that in this case, what we have is that the sum of Ti squared, okay, so the sum of Ti squared is then a harmonic sum. Okay, so this is roughly the sum of 1 over I. Okay, so it's a harmonic sum from 0 to k, so from 1 to k. Okay, and so this is roughly a logarithmic term in k. Okay, but we know that the sum of Ti, okay, will go to infinity. Or sorry, will not go to infinity. This is the sum of Ti squared will go to infinity, but the sum of Ti will roughly be equal to square root of k. Okay, so this is the summation of 1 over square root of I. And so if you work out the details, then with this choice of step size, with this choice of decreasing step size, like 1 over square root of I, then what will happen is that you will get convergence. So with Ti is equal to 1 over square root of I plus 1, or a certain constant times square root of I plus 1. Okay, you will get so the f best k minus f star will be less than something like log k divided by square root of k. Okay, so this is what you actually get. So if you look at this expression here, okay, so because we've seen that the sum of squares of the Ti will be roughly log k, and the sum of the Ti's will be square root of k. So this is what you will get as the convergence rate of your method. Okay, so in this case, this is what will happen. In fact, with the finer analysis, I think you can get rid of the log k, but it's okay. This is not so important. Okay, and so there are other kind of choices of step sizes that one can consider, but I will not I will not discuss it here. Okay, because these are typically the most used choices here. Okay, so what I would like to do now is to prove this this main inequality, the one that you see in blue here. Okay, and then what I will do is that I will just illustrate the method on a simple example. In fact, I can actually do this now because we have just discussed the choices of step sizes. So what you can see is that what I have done here is I have applied the subgradient method. So this is illustration of the subgradient method. So subgradient method. On the problem of minimizing the L1 norm of Ax minus b. Okay, so as I mentioned, this is a non-smooth function. I can construct a subgradient using the rules, the calculus rules I have showed you before. So this is the composition of the L1 function with a linear function. And so one can easily see that a subgradient is given by the vector A transpose the sign of Axk minus b. Okay, because remember the L1, the absolute value function, the subgradient is +1 if you're positive, is -1 if you're negative, and if you're at 0, you can choose anything between -1 and 1. So okay, so and I have tried three different choices of step sizes, one that decreases like 1 over square root of k, and two other choices of step sizes that are constant, okay, but with different magnitudes. So we can see roughly that what I have mentioned, what I have talked about before concerning the choices of step sizes. So first, if we kind of focus on the constant step size, if we first focus on this one, okay, this is the larger of the two step sizes, we see that it converges, it decreases, the value of the function decreases fast, but then it kind of oscillates around a certain interval, okay? It does not want to decrease anymore. And this is what I was saying, is that if you choose a constant step size, it will decrease, and then it will stay within a neighborhood, and it will not go down anymore, okay? So this is exactly what we observe with this red wiggly line, which corresponds to the choice of step size 0.001. If I reduce this step size more, then what I should get is I should get a bit slower convergence, but then the neighborhood around the optimal value should be smaller. Okay, and this is indeed what I observe. So I observe slower convergence, but then more stable, and then it converges to a lower value, and then it will actually plateau also around a certain neighborhood of the function value. Okay, and what you see in blue here, the last one is a decreasing step size with 1 over square root of k, and you can see that this is the best performance among these three methods. Okay, so it is the fastest, and it also should converge then to f star. But overall, you can see that this the behavior of this method is fairly slow. Okay, and also to find the right step sizes, I mean, this 0.001 and 0.001 and so on, this requires a little bit of tuning for each of your problems. So it's not always very easy to set up, and it requires a little bit of trial and error to get the right step sizes and so on. Okay, so let me maybe to conclude, let me just explain how one can actually prove this main result about the convergence of the subgradient, and that will kind of conclude our discussion of the subgradient method. So it's the proof is actually not going to be very complicated. So we just look at the we consider instead of looking at the function value, I'm going to look at the distance squared between the iterates and x star. So I have norm of xk plus 1 minus x star. So by definition of the subgradient method, this is xk minus tk gk minus x star squared. Okay, and then I'm going to expand this this square. So this is then the norm of xk minus x star squared, and then minus 2 tk gk transpose xk minus x star plus tk squared norm of gk squared. Okay, so I just wrote that the norm of a plus b squared is the norm of a squared plus 2 times a transpose b plus the norm of b squared. Okay, so now I'm going to use the fact that gk is a subgradient to try to simplify this this term here. So I know that so since gk is a subgradient of f at xk, okay, so what I know is that f star is bigger than f of xk plus gk transpose xk minus x star. Sorry, so this should be x star minus xk. Okay, and so what this implies then, so this implies that that gk transpose x star minus xk is less than f star minus f of xk. Okay. So so then continuing from the yellow piece here. So let me just, okay. So continuing. So this will give me this is less than. So this is less than the norm of xk minus x star squared plus tk squared norm of gk squared. Okay. And then I have here plus 2 tk times f star minus f of xk. Okay, where I just used this inequality. Okay, so now okay, so let's recap. Let's rewrite this inequality here. So this is xk plus 1 minus x star squared is less than norm of xk minus x star squared plus tk squared norm of gk squared plus 2 tk f star minus f of xk. So now this term, this guy here, okay, I can iterate, I can apply the same type of bound on this guy. So I can bound this by norm of xk minus 1 minus x star squared plus tk minus 1 squared, norm of gk minus 1 squared plus and so on. Okay, so using the same bound, on norm of xk minus x star squared, we get, okay, and then going all the way up to 0, what we get at the end is that the norm of xk plus 1 minus x star squared is less than the norm of x0 minus x star squared plus the summation of ti squared norm of gi squared, I going from 0 to k, plus 2 times the sum from I equals 0 to k of ti f star minus f of xi. Okay, so now it's just now a matter of rearranging the inequality. Okay, so this guy is non-negative. Okay, so I'm going to move things to the other side. So this implies then that the sum of ti times f of xi minus f star is less than the norm of x0 minus x star squared divided by 2 plus the sum of ti squared norm of gi squared divided by 2. Okay, so now I define, let's record that f best k is the minimum of f of x0 up to f of xk. Okay, so what I can write definitely is that f best k minus f star. Okay, so this is the minimum of the f of xk minus f star, and so in particular it is smaller than the average of these values, and so this I can say that this is less than 1 over sum of ti times the sum of ti f of xi minus f star. Okay, so this is, if you want, so this is an average, a weighted average of the f of xi minus f star. Okay, but then by the previous consideration, this is then going to be less than norm of x0 minus x star squared divided by 2 sum of ti plus plus the sum of ti squared norm of gi squared divided by 2 sum of ti. Okay, and the last thing that we're going to use, so this is exactly what I wanted, the last thing that we're going to use is the fact that, so this 2 sum of ti plus g squared sum of ti squared divided by 2 sum of ti. is to use the fact that if f is G Lipschitz, then the norm of the GIs is going to be less than G. Okay, this is exactly the same thing as saying that if a function is G Lipschitz, then the gradient of the norm of the gradient is at most G. The same proof exactly follows for the subgradient. Okay, so you can show that if a function is G Lipschitz, then the subgradients all have norm at most G. And this is what allows you to bound this norm of Gi squared by G squared. Okay. So this is essentially the proof of this inequality that I showed earlier. Okay. So to summarize, then the subgradient method is a very simple method that you can implement in just one line. I mean, computing subgradients is usually very easy, and so it's a very simple method, but its performance is not very good. As I mentioned, it requires a bit of the choice of step size is crucial. So it's typically not a method of choice unless you don't have anything else to do. There is, I did not talk about this, but there is you can also do a projected subgradient method. The proof is very similar. So if you want to minimize a convex function, a non-smooth convex function on a convex set, you take a subgradient step and then you project back on your set C. The proof, the convergence proof is exactly the same and so on. Okay, so this I will. This is all I wanted to say for this afternoon session. Tomorrow we will look at some better methods to handle non-smooth functions. So functions that exploit the structure of the objective function. As I mentioned, if your function is composed of a smooth term and a non-smooth term, we'll see how to exploit such a structure. And these methods are typically much better than the subgradient method. Okay. So I guess I will stop here, and if you have questions, then please put them on the chat, and I will try to answer them.
Thank you very much, Hamza. Are there any questions that you could write down on the chat area, please? There were some questions, but if you have more.
Does choosing a bad subgradient affect the complexity of the algorithm? Yes. I mean, it can affect, so the global complexity. So as we mentioned, I mean, if you, let's see. So what we've shown essentially, maybe I didn't write it down explicitly, and this also answers the question that follows. What is the complexity of the subgradient method? So the subgradient method allows you to get, after k iterations, you get an accuracy of 1 over square root of k. Okay, what I have shown is if you choose the step sizes to be 1 over square root of k, then the iterations f best k minus f star is going to be roughly log k divided by 1 over square root of k. The log, you can actually get rid of it. I did not explain how, but okay, it's not so essential. But you can get a 1 over square root of k iteration complexity. Note that this is much worse than the gradient method, which is 1 over k, and even worse than the fast gradient method, which is 1 over k squared. Now, does choosing, I do not actually know if one has access to the whole subdifferential of a function at any point, if one can achieve a better complexity. This, to be honest, I do not know if this has been studied. Probably it has, but I do not know what the answer is. But it is true that at least from simple considerations, I mean, the simple example I gave of the absolute value function, already if you can check if 0 belongs to the subdifferential, then you can stop. Okay. Unlike if you just take kind of one subgradient, then this subgradient indeed might be bad, and it might lead you off from the optimal point. So yes, so I would say yes, that having access to the full subdifferential should be able to help you at least to be able to detect if you're close enough to the solution, how close enough you are to the solution. Even though most methods that are used, let's see. I mean, it would be actually quite expensive to compute the full subdifferential. So yes. So okay, so actually, Abdulrahman, what happens to non-smooth algorithms from efficiency viewpoint when the function happens to be smooth? Yeah, so if the function is smooth and I apply the subgradient method, yeah, so if the function is actually smooth, then the subgradient is the gradient method, and so you get what you get is just the gradient method. But then the thing is that the analysis of the gradient method relied on this L smoothness condition, and that the gradient itself is L Lipschitz and so on. So yeah, so I mean, yeah, the subgradient method just reduces to the gradient method in the case of a smooth function. I think, does this answer the question?
Yes.
Yes. Maybe a general purpose question: does the span of optimization design space affect the optimization speed? Okay, I'm trying to see if I understand this question. Okay, I'm not sure I understand this question. I don't know if Abdulrahman, you can.
Maybe we could ask Yunus to make his question more precise.
Mm-hmm.
Okay, hello.
Hello.
And thank you for these great lectures. So my question, for example, let's assume we want to optimize 1D function in an interval -1, 1. Assuming we change it for -5, 5, does it affect the speed?
Oh, you change the okay, the span of the optimize. So you rescale the function. I mean, it depends on which algorithm that you use. I mean, I mentioned yesterday something very similar to what you're talking about. So where I scaled a certain variable and I showed that the gradient method, this will impact the performance of the gradient method. So you might get some oscillations. I mean, remember this example of the ellipses that I had and this oscillating gradient method. Essentially, if you rescale just one variable a little bit by 1/gamma, then these oscillations will go away and you will converge immediately to the optimal point. Okay, so the gradient method is indeed affected by the scaling of the variables. Later on, we will see on Thursday, we will look at the Newton's method. Newton's method is a method that is not affected by the scaling of a function. The subgradient method is affected by the scaling of a function. Yeah, so it depends on which method that you use, and obviously it is desirable not to have a method that is not depending on the scaling. So. So maybe I can say something. I mean, just to kind of answer a question about if I have the full subgradient. So if I have the full subdifferential of a function at a certain point, I can actually Oh, I mean, there always exists in the subdifferential a direction that is descent direction, but finding which descent direction, which direction is a descent direction is not easy. It involves another optimization problem. But if you can afford doing such an optimization problem, then yes, it may be worth actually taking this specific subgradient and to use it in your iterates. But I do not know from a complexity point of view if this will allow you to, say, change the square root of k to 1 over k, for example. This may be possible, but I do not know the answer to this one. Yes, that also answer. I mean, someone else, can you give some best practice to choose the appropriate gradient? I mean, if the gradient is defined, there is no choice. I mean, the gradient is just the gradient. You don't have a choice. But yeah, if you have a choice of subgradient, then you might consider choosing a descent direction. I mean, there is a way. Among all subgradients, there is one that's going to be a descent direction. But this involves doing another optimization, which itself is hard. So this is not typically done. This is not something that we typically do. Oh, I see. Among others, make this method more or less probabilistic. Yes. Yeah, that's kind of a hard question. I did not think about this before. So typically, yeah, I did not see such an analysis before, where if you choose the subgradient at random from the subdifferential, and then analyze this stochastic process. I have not seen such an analysis done before, even though that would be interesting. The kind of stochasticity in optimization usually comes in the form of your function itself is an expectation of a large number of functions, and you kind of sample at random from your function. Okay, you compute this expectation by an empirical expectation, and you compute a gradient or a subgradient in this way. And then this is how you get a stochastic process that you need to analyze. But choosing the subgradient at random, this to be honest, I did not see it done before. If it is studied, and how does it perform? Yes. Is it possible to choose a new T to enhance the performance of subgradient method? So T, I guess you're meaning by T is the step size. So I mentioned the step sizes that one would choose in a subgradient method that typically get the best rate is 1 over square root of k. Now, there is kind of, if you have some additional information about your function, and in particular, if you know the optimal value. So if you happen to know the value f star, not x star, but if you just know what f star is, then there is something called the Polyjack step size, which is a way to choose the step size, and is actually very nice. It's a very nice choice of step size that give you typically very good convergence rates. But this is only depending, I mean, this is only if you know f star, which in many cases we do not know. But if you happen to know this, this is a very good choice. I mean, otherwise there is a, I mean, I only discussed two possible choices here, the kind of the constant step size and 1 over square root of k, but there is kind of more longer discussions about how to choose the step size for a subgradient method. Maybe I will put a reference to this kind of discussion when hopefully I put this slide online. I will kind of put, there's in particular a well-known kind of some lecture notes by the group at Stanford that discusses how to choose the step size of the subgradient method. Maybe I can actually, let me put it right now. So discussion on step size, detailed discussion on step size choice and subgradient method. oops, sorry, this is, I should send to everyone. Very good. So I put a link to some lecture notes online that will give you, that will discuss kind of more at length. I mean, here I was a bit, I mean, it was a bit quick, a discussion of how, of the effect of the choice of step size on the convergence. Okay. What is the best norm? Well, there is no norm to choose in optimization. So, I mean, this is, I mean, if you're asking about the modeling, I mean, the norm is something that comes from your problem. So you want to minimize the L1 norm, the L2 norm, the LK norm, whatever norm that you want. And then depending on which norm you choose, then you choose a different optimization algorithm. So the L1 norm is not smooth, so you have to use a non-smooth method. The L2 norm is smooth and strongly convex and so on. So this is how you would choose this.
Morji, did you raise your hand to ask oral question, or is it a mistake? No? Okay. If there are no more questions, we say thank you to Hamza for this nice lecture again. And
thank you.
We schedule the next meeting for tomorrow.
Okay, tomorrow same.
François Delarue will chair, will at least have some co-hosting of the session with you.
Okay. Mm-hmm.
And then I try to meet you during the session of the morning, and if not, it will be in the afternoon.
Okay.
But in any case, thank you very much.
Yeah, no problem. Thank you again. Thank you.
Take a rest now, and yes. Let's meet again tomorrow.
Tomorrow morning.
Bye-bye, everybody.
Okay, bye-bye. Thank you. Salam alaikum.